Hi, it's time for another math easy solution. Time to discuss further into polar coordinates and look further into the area formula, and now look at a general formula for the area bounded by two curves. So let's just jump right in. So the area bounded by two polar curves, in my last video, example 2, that illustrated the procedure for finding the area bounded by two polar curves. That was basically an example, and now we'll look at it in more general terms. So in general, let R be a region as illustrated in the figure below, and I'll draw that soon, that is bounded by curves with polar equations R equals f of theta, and R equals to g of theta, and theta equals A, theta equals B, where f of theta is greater than 0, greater or equal to 0, and the angle is B minus A. The difference is between 0 and 2 pi. So in other words, what this all means is if we were to draw a polar axis like here, here's the origin, draw a polar axis across here, and now what I'll do is I'll draw the R equals to f of theta function. I'll draw this in red. Let's say we have something that looks like this, and this is our R equals to f of theta. And now let's draw in blue R equals g of theta. Let's say we have a function that goes something like this. Should draw this a bit better. Let's say something like that. So let's say this function right here is our R equals to g of theta, like that. Yeah, so we have these two functions like that, then they're polar curves, and now we want these angles, theta equals A and theta equals to B. Let's say theta equals to A somewhere across like this. Yeah, like this. So let's say, okay, this angle right here is theta equals to A, and it cuts through these two functions like that. And now we have, let's say we have the other angle, theta equals to B, across right here. Yeah, this one's right in through that intersection, doesn't need to be. Let's say this is theta equals to B. So this means that the resulting region is R right here in between these two curves, R equals f of theta and R equals to g of theta. Yeah, so now if we want to determine the area, well, the area of R is found by subtracting the area inside R of theta, so this entire red region, from the area, actually no, R of g theta from the area R of f theta. So we want to subtract this overall region across here from the overall one all the way across like this in the red one. Yeah, alright, so I just erased those little lines so you get the picture. So we'll just have to subtract the two areas, and again, first of all, recall that the area formula for a region within a polar curve is equal to A is equal to A to B of 1/2 R squared d theta. So recall this, put this in a little cloud, like bubble, just for a refresher. So now this area of this region R is equal to, so I'll write A equals to, I'll write the area of the F underneath the F function minus area underneath the G function. So this equals to integral from A to B of 1/2, and now the R squared is R is f of theta, so we have this f of theta squared d theta, then minus integral from A to B of 1/2 g theta squared d theta. And now since we're doing the integral from the same A to B and A to B, and also we have the halves, we could simplify this into A equals to 1/2 the integral from A to B of f of theta squared minus now this g of theta squared, like that. And then I'll put a bracket all over and then write d theta. So this is our general area for a region bounded by two polar curves. Yeah, but now I want to make a caution about this. Is basically the fact that a single point has many representations in polar coordinates, so you got to beware of that, sometimes makes it difficult to find all the points of intersection of two polar curves. For example, this one right here might be hard to find this point because it could occur at different times for both functions. Yeah, basically, for instance, it is obvious from the circle and cardioid of example 2, so make sure to watch out, put that in the video link below. Shown below here, also just recap it there, that there are 3 points of intersection. So this graph is from example 2, so we had the circle is in red right here, r equals 3 sine theta, and now we have the cardioid over here. But in that example, I showed that the 2 points of intersection, well, I got these 2 points, but it's clear that this one is as well. So this one I'll call this 1, 2, and that's the third right there. But however, in example 2, we solved the equation r equals 3 sine theta and r equals 1 plus sine theta and found 2 such points. This is 3 over 2 pi over 6 and 3 over 2 5 pi over 6. Basically what I did was to find 1 and 2, I set these two equal to each other so that we have 3 sine theta as the circle equals to the cardioid, 1 plus sine theta. Move this over to the other side, we get 2 sine theta equals to 1. In other words, we get sine theta equals 1/2, and in this case we had theta equals to this exact ratio is theta equals to pi over 6 and as well as 5 pi over 6. This is within 0 to 2 pi. For theta, I'll write this for theta is between 0 and 2 pi, like that. And also to get this 3 over 2, I didn't do that before, but you could easily plug that in. R equals to, let's say, 3 sine pi over 6, that just equals to, or 3 sine 5 pi over 6, that's the same thing as writing 3 over the ratio 1/2, this equals to 3 over 2. And likewise, r equals 1 plus sine theta, we get 1 plus 1 over 2, times this by 2 over 2, the same thing as writing 2 over 2 plus 1 over 2, adds up 3 over 2. So that is the r values, just for reference. So yeah, from example 2, I showed that you can only find the 2 intersection points here and here, but this one here is a bit tricky. Basically, the origin is also a point of intersection, but we can't find it by solving the equations of the curves because the origin has no single representation in polar coordinates that satisfies both of the equations. But notice that when represented as 0, 0, as these coordinates are 0, pi, the origin satisfies r equals 3 sine theta, and so it lies on the circle. Basically, first of all, you could just see, recall just a sine function. It looks something like this. This is theta. This is sine theta. It goes up and down like that, etc. So it is 0 at here, and this one is at pi. That's also 0. So we have r equals to let's say 3 sine 0. This equals to, well, that's a 0. So 0. So now we have a 0, 0, and likewise r equals to 3 sine pi. This is within 2 pi. You could also put 2 pi in there as well. This equals to, well, 0, and that just goes to, well, 0. Now the r is 0 for the angle is pi. Yeah, so that point is on the circle, and now when represented as 0, 3 pi over 2, it satisfies r equals 1 plus sine theta, and so it lies on the cardioid. Basically right here, r equals to 1 plus sine theta sine 3 pi over 2. So let's look at that value. That value is right over here. This is the third, that's 270 degrees. That's over at here. This is at -1 for sine. So this equals to 1 minus 1 equals to 0, like that. So now this point is 0 and 3 pi over 2. So that means that this is the origin right there. And this is, that's for the cardioid formula, but for the other one we have this, you could also add the 2 pi as well. So now a good way to try to wrap your head around this is basically think of 2 points moving along the curve as curves as the parameter value theta increases from 0 to 2 pi. On one curve, the origin is reached at theta equals to 0 and theta equals to pi. On the other curve, the origin is reached at theta equals 3 pi over 2. The points don't collide at the origin because they reach the origin at different times, but the curves intersect there nonetheless. So the curves are there, but the actual point don't touch it at the same angle at the same time. Thus, to find all points of intersection of two polar curves, it is recommended that you draw the graphs of both curves, and it is especially convenient to use a graphing calculator or computer to help with this task. And now to show you how this changes in different times, right here, I've actually updated the graph from example 2 right here, and to include the point. So let's just click this. Yeah, so here it's loading, so Desmos calculator is quite amazing. So what I've done right here, here are the points across there, and what you can do is, here is r equals, this one is that graph overall, this circle, r equals 3 sine theta. Here is the cardioid over here, r equals to 1 plus sine theta. But now if you put these in Cartesian coordinates or parametric form, so you just put this r times cos, and then the r times sine, and likewise for both of the two functions, but I put a instead of t so that we graph a single point. And now you could change from 0 to 2 pi. Here is the point on here. This one is the point on the cardioid, and at the exact same time we have this point is on the circle. Let's just move this over. So notice it collides right there. Let's go to 0. So here's a start off at 0 over at the origin, and over here at 1 for the cardioid. Let's just press play. Yeah, so notice they have different times. Let's slow this down. Let's slow this down and start off from 0 and play. So notice this, they're going to intersect right there at the exact same time. And now they're going all the way around. They can intersect here at the exact same time, but then the cardioid starts to slow down over. Well, it is pretty slow over here. Yeah, it's slow there. Notice this one touches here, so it already passed the origin. It's still going, and this one finally touches it there at different times. So this is a great illustration of it. Let's make this in projector mode. Make it bigger. Yeah, so now this one's gonna reach it, and yeah, there it goes back. That's at I think that's 2 pi. Now it's going back towards it. Now this one gets back to it. So let's speed this up. So this is pretty amazing calculator. So yeah, this is absolutely amazing. So yeah, you could play around with that. It's quite amazing. And anyways, that is all for today. Hopefully you learned from this, and yeah, it's very interesting. So you always have to graph it to double check if they actually have more than just the intersection points that you can just solve. Anyways, that's all for today. Thanks for watching, and like always, you can download these exact notes in the link below, as well as these notes will be on Steemit shortly after I upload this video. Anyways, thanks for watching, and stay tuned for another Math Easy solution.